Alright, I'm going to see if I can explain a little bit of these last few problems. So this is number 51. So first thing you do is, of course, find the partial derivative with respect to x. So we're probably good. We got that right there. And then partial derivative with respect to y there. And then set them equal to 0. And this one, if you set equal to 0, you can factor out a y. So then you can see that y equals 0, and then you can set this little factor equal to y, and you can get y equals 3 minus 2x. So then what we can do is we can take each one of them separately, we can plug them into the other partial derivative. And so let's take the 3 minus 2x and let's plug it in right here for the y. So you can see what we get. We got all x's, so we end up solving for that, and we get x equals 0, and hold on, this dumb thing. Okay, so x equals 0. I don't want it to ask me again. Let's see. Do you want to save? Let's see. Hold on. Would you like your? No. Okay. So I got x equals 0 and 1, and then I take those and I just plug them in right here to get what the y values are to go with it. So 0, 3, and 1, 1. So we got a couple critical points out of that. Alright, then we could also have y equals 0. So we could do the same thing, and we plug in 0 into the other partial derivative, and we get, oh man, this is hard to scroll. Okay, so then we get this here. Plug in a 0 right there. This is really funky. Alright, so plug in a 0 right there, and we get an expression. You can see from that we're going to end up getting 0 equals, or x equals 0, and x equals 3. So when we plug those back in, we already knew that the y value was 0, so we got 0, 0, and 3, 0. So we got those critical points to check out. And then we want to go ahead and do figure out the other pieces, because we need to figure out we're going to use the second derivative test. So you've got the other pieces. We have the partial derivative with respect to x twice. Okay, so there's the work shown there, and the d, so we're finding the d, and I just have an expression for the d, so it's these two multiplied together minus this one squared, and started plugging the numbers in, plugging in our critical numbers to see what we got. So for the first three, we got d is less than 0, which tells you that those are saddle points. So, and then when you take the 1, 1, you plug that in, you got 3. So that's bigger than 0. So then the second part is then you plug that same critical point into the second derivative, which is this one here. And you plug that 1, 1, plug it the 1, 1 in there, the second derivative, and you end up getting negative 2 times 1, which is negative 2. When the second derivative is less than 0, remember, less than 0, whenever the second derivative is less than 0, that's a maximum, just like your single variable calculus. Alright, so I think we're good on that one. Let's try another fun one. 53. Okay, so first thing you do is find the critical points that are inside of this triangular region. So you can see that how we do the same thing we did before. Partial derivative with respect to x, partial derivative with respect to y. Set them both equal to 0. And we got y equals 0, but that's not actually inside D, that's actually on the boundary. So we're trying to find the ones that are inside first. And then you can see the work here. y equals 4 minus 2x, and then we can take that and substitute it in. Now that was a lot of fun. I was really surprised how much fun that was to try to make that work out. So anyways, I think I lost a little bit of it on the end here, but you can see the work, and it actually did work out. And you end up getting your critical numbers that way. So we get x equals 0, which again is not inside D, it's on the boundary. And then we have x equals 1 and x equals 2. Now when we plug it back in to get what the y value is with that, we end up getting 2, 0, which is also not inside the D, it's on the boundary. So the only one we're going to check right now on the inside is 1, 2, and f of 1, 2 is 4. Right there. Alright, so we're good on the inside ones. Now we get to check the boundaries, and that's the super duper fun part. So now we check the boundaries, which are lines. So let's check the first one, L3, which I have labeled L3 is that's the vertical one. So that's x equals 0 that whole time, it's fixed, and the y value is allowed to vary from 0 to 6. Well, it turns out when you plug in a 0 for the x and you let the y be y, it turns out to be 0, because they all have every little component has an x in it, so it turns out to be 0. And then similarly on L1, same thing. If you notice, the y is always 0, and the x can vary from 0 to 6, but it doesn't really matter because you plug it in, you end up getting 0 on that whole line too. So the only one that's a little bit interesting then is that line, sort of diagonal looking line, that one there. And so we need an expression for that, and so we just kind of use our slope-intercept method there. We can tell that we're going, down 6. Whoops, we're going down 6 and over 6. Down 6, over 6. We can tell the slope is -1. And then you can see the y-intercept is 6. So we got an expression. Y equals -x plus 6, or I'll just go along with how the solutions have it. They have x equals 6 minus y. So then we're going to say for the x, we're going to plug in 6 minus y. And for the y, we're going to let it be y in the original function. So in the original function, look at all this fun we have here. Plug all that in, and we end up getting, it looks like I cut off a little bit at the bottom. So let's see here. So we end up getting this expression, right here. So we end up getting that expression, and then we want to find the derivative of that to find the critical points. So the derivative is 6y squared minus 24y. And then set those equal to 0. That got cut off a little bit. So that equals, what do we got out of that? So we got 0 and 4. So y equals 0 and y equals 4. And then you just want to find the x coordinates that go with that. So boom, plug it in there. So we end up with 6, 0 and 2, 4. So then we can check those out. So we get f of 6, 0, which is 0, and we get f of 2, 4, which turns out to be -64. And so we got the absolute min, of course, is right here. So this is the absolute min. And we got the absolute max was f of 1, 2. And that was our critical number we checked before. Remember that? So hopefully you remember that. Alright. Last problem, but I just want to make this so it's not too long of a video. Last problem, we get to use our method. Alright, so we set the regular function gradient equal to lambda, the gradient of the constraint. So there we go. It's set up. And we set up our little equations and make sure that it satisfies the constraint as well. So when you set them equal to each other, we get, let's see what we get. We get this. And logic would say, when you look at the left and the right side, that only a couple of things can happen. it looks like the y has to equal lambda for the left side to equal the right side, of course. It's the only thing that's even different. So y equals lambda, or if I said, lambda equals y, then I can plug it into the other equation. So I'm plugging it in right there. So that means that x squared equals 2y squared, and that means I can substitute that into the constraint. So the constraint being, x squared plus y squared equals 1. So when you do that, you get 2y squared plus y squared equals 1, and then eventually you get y equals plus and minus 1 over radical 3, and then you can plug that back in to figure out what the x is. You can plug it in. I plugged it in, let's see, I did x squared equals 2y squared, so I kind of went up to this step and figured y squared is 1/3, so 2 times a third. It's a little bit easier. So then you got x squared equals 2/3. Take the square root, plus and minus, square root of 2/3. You end up checking those. You'd have to plug them into the original function, and you get your absolute maximum and minimum. And the other case was that x equals 0, but that doesn't really work out, because if x equals 0, then somewhere in here, let's see, hold on. If x equals 0, it just doesn't work out, because if x was 0 right here, then the y would have to equal 0. That's the only way for that to equal 0, and that wouldn't work, because we have to have it equal the constraint. It has to be x squared plus y squared equals 1. All right, cool beans. Hold on. Where's my?
That was easy.
Yeah, right. Okay.